So let's go through an example problem. In this problem here, we have a train. They tell us the train is moving between two stations. They give us a velocity time graph for this train moving. You can see on the x-axis we have time in seconds. On the y-axis we have velocity in units of feet per second here. We can see we start at 0, 0 down here, increases up here until we get to a time of 30 seconds. It reaches 40 feet per second velocity. It stays at a constant velocity of 40 feet per second between a time of 30 seconds and 90 seconds. And then when it reaches 90 seconds, it decreases its velocity all the way back down to 0 by the time it gets to 120 seconds. So they want us, from this graph here and the given information, they want us to plot an acceleration time graph and a position time graph over the same time interval from 0 to 120 seconds. So now that we've had a chance to read through the problem statement and understand what they've given us, what they're asking for, the next thing that we want to do is draw out our first setup sheet here, where we clearly label all of that information into one location it's easy for us to reference back to. So the first thing we do is say, what do they give us in the problem statement? Well, in the problem, they really just give us a graph for this simple problem here. So we have our velocity time graph, we redraw that out, and now we put up our chosen coordinate system, where we choose x to be positive to the right and y positive going up. And that's to help us with our sign convention as we're going through the problem. So clearly having the given information, the given graph, and a chosen coordinate system is great for us as we're going through different steps of solving this problem to reference back and remember what we chose and what was given to us. The next thing we want to clearly write down is what they're asking us to solve for. So in this case here, they're asking us to draw an acceleration time and a position time graph from the given information in the problem statement. So what we want to do when we look at one of these graphs is to deal with each time interval separately. So we want to look at this from 0 to 30 seconds, where we have an increase in velocity with respect to time, from 30 to 90 seconds, where we have a constant velocity with respect to time, and from 90 to 120 seconds, where we have a decrease in velocity with respect to time. So that's what we do down here, is we go through these individual time intervals. So as we look at these time intervals, we're going to start with the first one, which goes again from 0 to 30 seconds. We have an increase in velocity with respect to time. So look at this here, we say 0 less than or equal to t, less than or equal to 30 to denote that interval there. We know we have an acceleration. An increase in velocity with respect to time, which we see here is an acceleration. Acceleration is given by the relationship dv dt, change in velocity with respect to time. So what do we have here? Well, our change in velocity here, we go from 0 to 40. So 40 there for the change in velocity. Change in time, dt, is from 0 to 30. So we go 40 over 30 here. Reduce and simplify, this is 4/3 feet per second squared as our units. So again, feet per second, time in seconds, we have an acceleration of feet per second squared. So now we take a look at the second time interval, and this goes from 30 to 90 seconds here. So we look at this here, we go 30 less than or equal to t, less than or equal to 90. Now we have an acceleration equal to 0 because we have a constant velocity. Constant velocity means 0 acceleration, so a is equal to 0. And last, we look at our time interval from 90 to 120 seconds on our graph here. And you can see we decrease our velocity with respect to time, starting at 40 feet per second all the way down to 0 feet per second when time is 120. So we have our change in time and we have our change in velocity. So we say a is equal to dv dt, change in velocity with respect to time. So we go negative because now we're going down in velocity. And we've denoted up here that positive in the y direction is going up. So this is where sign convention becomes important, and it's great to have our chosen coordinate system right here so we can reference back to it. So this is negative 40 over 30 here. So this is, reduce this down, simplify, negative 4/3 in the same units of feet per second squared. So now we have an acceleration for the first time interval, second time interval, and third time interval, which is what we need as the acceleration information in order to plot this acceleration versus time graph. So with that acceleration information that we just obtained for each of the time intervals, 0 to 30, 30 to 90 and 90 to 120 seconds, we now have the acceleration information. So we redraw out our graph here, choose a given coordinate system up here. So we're saying x positive to the right, y positive going up again. We have our acceleration now on the y-axis and our time on the x-axis. So it asks us to plot this with respect to time still in the same time interval. So on our x-axis, nothing's going to change between our acceleration, velocity, and position graphs. What is going to change is our y-axis here. So now this goes up, and we saw at the beginning we had a positive acceleration of 4/3 feet per second squared. So we draw that in here, and that's a constant acceleration there. Then that was the first time interval from 0 to 30 seconds, and our second time interval from 30 to 90 seconds, we saw that we had a 0 acceleration. Constant velocity is 0 acceleration, so from 30 to 90, this stays right at 0 right here on our y-axis in between these two x-axis points of 30 and 90 seconds. And lastly, in the time interval from 90 to 120 seconds, we saw that we had a decrease in velocity, or a negative acceleration. So this was at negative 4/3 feet per second squared. We draw that out here. So this is the first part of our solution, our acceleration time graph over that same time interval, clearly labeled with our chosen coordinate system here. So the area under the curve represents the displacement. So next we want to calculate out the area separately for each time interval. So this is how we're going to get to our next part of our solution. So in order to solve the last part of this problem, I want to flip back and be able to reference that graph, my given graph, from page 1. So this is why I really like to have that page 1 of just the given information on its own with a clearly labeled coordinate system, because now I need to reference this in order to solve for the third part of the problem, where they ask us to solve for the position versus time graph. We want to look at this first graph here for our velocity versus time graph here and calculate the area under the curve in order to get position from this graph here. So we do that there. We go back to our velocity versus time. Let's look at the first interval from 0 to 30 seconds here. So the area under this curve is right here in this triangle right here that I'm going to shade in right here. So we have 0 to 30, so we have a distance here of 30, and then we have a distance up here of 40. So we recall the area of a triangle is 1/2 the base times the heights. So I draw that in here. For this time interval is 1/2 of 40 times 30 there. So this is equal to 600 feet. Now I do the same thing here from the time interval from 0 to 30 seconds, calculate the area under here. So this whole rectangle here, so base times height. So we go up from 30 to 90 is a distance of 60, and our height of 40 there. So we go back up here, draw out, okay, area is 60 times 40, or 2,400 for our area under that there. And then lastly, we come down here to the last time interval from 90 to 120 when we look at this here. So there is our distance, the difference there is 30. And now we have our units up here of 40 times 30 times 1/2 to get the area under of a triangle. So we have this here 1/2 40 times 30, or 600. So now with all this information that we've obtained from the first graph here for our position versus time information, we can add these area calculations for each time interval together to get the total area. So now we can take this information that we got here for our position versus time for each of these intervals here from 0 to 30, 30 to 90, and 90 to 120, where we go 600 feet, another 2,400 feet, and another 600 feet. So we want to break this down now and draw our position time graph from that there. So we draw this out, same time interval, 0, 30, 90, 120. We know that at 30, we've gone 600 feet. At 90, we've gone 3,000, because that is our 600 plus our 2,400. We've gone an additional 2,400 past the 600 in this time interval here. And we go another 600 feet past the 3,000 to 3,600 when we reach 120 seconds. So we draw out these 3 dots at each of those points there. So at 30 seconds, we have 600 feet. At 90 seconds, we have 3,000 feet. And 120 seconds, we have 3,600 feet. We still have our coordinate system labeled here, positive x to the right, positive y going up here. So now we want to think about this. If something is accelerating in the beginning, we're going to see a curve going up like this for an acceleration. We're going to see if there's 0 acceleration, this is a straight line from there to there. And as it decelerates in the last from 90 to 120, we have a curve going in this direction there. So that's how we draw out our position time graph. And to get into the details here of the curve shape, straight line curve shape of this here, what we have down here is a little cheat sheet here, which we can reference. We look at the velocity and acceleration to tell the shape of the curve. So is it increasing at an increasing rate? Well, that's what we have here. Is it increasing at constant velocity? That's what we have in the second part here is a constant velocity. Decreasing at a constant velocity. Well, we didn't have that in our graph or our problem here, but we did have increasing at a decreasing rate for our deceleration right there. So this is something to always reference back to when we're drawing out our position versus time graphs here if we want to know the shape of the curve.